Today we're going to talk about applied maximum and minimum problems. Now that's a fancy way of saying we're going to do word problems. So let's do applied max and min, and what we're going to do is we're going to use derivatives to find out what the maximum and minimum or minimum of certain questions would be. The easiest one I can think of, or an easier one, would be something like, let's say we have 40 inches of rope, and we want to make a rectangle that has maximum area with our 40 inches of rope. Okay, so this is one that you can put together pretty easily. Here's what we're going to do. We're going to create a rectangle. Now I have no idea what size it is. First, I'm going to label this X, this Y, this X, and this Y. Now what I know about having 40 inches of rope is that I've got 2 X's and 2 Y's equal to 40. So that's something that relates. In fact, I could divide each part by 2, and I would know that X plus Y is equal to 20. So that's a relationship between X and Y. Now that is not the area, obviously, that's just the outside. So we're talking perimeter, we're not talking area yet. But this says find the maximum area. So what's the area of this rectangle? Well, area is equal to length times width, which in this case is X times Y. Now, if we want to deal with this, we've got way too many variables. So let's get rid of one of them. And in this case, it's pretty easy to do because we know a relationship between X and Y. We know that Y is equal to 20 minus X. So I'm going to put that in here. So this is equal to X times 20 minus X, which is 20X minus X squared. Now you don't have to multiply it out, but sometimes that helps. So the next thing I'm going to do is I'm going to look at this area compared to this value or this process, and I'm going to maximize it. How do I do that? I take the derivative. So let's take dA dx. The reason I'm doing dA dx is I'm taking the derivative of the area equation using x as the variable, or with respect to x. So here I'm going to take the derivative of 20x, which is 20, and the derivative of minus x squared, which is minus 2x. Then I am going to try to find the critical values. As maximum and minimum values tend to be at critical values or at endpoints of whatever, the domain or whatever. So let's find critical values. Critical values on this one, well, there's only one. 20 minus 2x equals 0 if x is equal to 5. Okay, so and I can't divide. Let's try that again. If x is equal to 10, okay, 20 equals 2x, and so x is equal to 10. Sorry about that. All right, so that's a critical value. Now, let's figure out the domain. Now, I know I sound like an algebra person doing that, but what are the possibilities for x? We've got 40 inches of rope, and we've got to put it in a rectangle. So at the very minimum, x can be 0. So x is somewhere between 0. Now, if it is 0, that's kind of ridiculous because we would not have a rectangle. And the very biggest it could be would be what? How about 20? Because we've got to have 2 of them. So the very biggest it could be is 20. And that wouldn't be a rectangle either. But those are the smallest and largest values possible for x. Thankfully, our critical value is in this region. So let's find out the area at 0, at 20, and at 10. So the area function, not the derivative, but the area function when x is 0. So the area of x is 20 times 0 minus 0 squared is 0. So the area is 0 if x is 0. If x is 20, we've got 20 times 20 minus 20 squared, which is also 0. Now at the critical value, when x is 10, we've got 20 times 10 minus 10 squared. That's 20 times 10 is 200, minus 100 is 100. Now how do I know that's the maximum? Let's try something we've done in derivatives. This is the area, and we hope that it's the maximum. Obviously, it's a lot bigger than this one and this one, but let's go through and find it. Let's use the second derivative test. So the second derivative test is where you take the second derivative, so d squared a dx squared. This is take the derivative twice of a using the variable x twice. So I go back up here to the derivative. It was 20 minus 2x, so the second derivative is minus 2. Now this may seem a little strange, but we have to put 10 in for x. Well, that's impossible in a way because there is no x. So we do that. The notation looks like this: d squared a dx squared, where x equals 10 is equal to minus 2, and there's no x, so it's negative. That is concave down, remember, and if it's concave down, things that are concave down have tops, so that implies that there's a maximum. That's a second derivative test. So our value was a maximum. So we just proved that it was a maximum. So what we say is that this rectangle has a maximum area of 100 when x equals 10. Now something else you and I need to do is we need to figure out what y was. Well, what was y? Up here we have y is equal to 20 minus x, so y equals 20 minus 10, which is also 10. Now something you might have noticed or thought about is the fact that the maximum area will be when it's a square. Yes, it is. X and y are both 10.